Hi, I'm adding this video into the playlist right after the free body diagram, and I think this might be useful because I want to kind of further enhance the idea of looking at a free body diagram and understanding vectors a little bit more so that, yeah, and then kind of tie it to a real world application, helps you play with a little bit of math, understand the vectors, and I think it's just an important idea that I want to convey with vectors, and I'll also insert a piece around energy and work with me through this. It might be a little bit tedious, so pay attention. Um, Set context. We've done regular vertical motion up and down. You know it very well. If something goes up, you can write S is equal to u t plus half a t squared with u, and the final velocity is 0 and acceleration is negative g. So you can come up with those values to calculate distance. Um, Likewise, if it's a free fall, u is 0. You have final velocity, which you can calculate with positive acceleration due to gravity. You can calculate S, all kinds of formulae there, which you can play around and very easily solve. You also know those formulas: convenience, v squared is equal to u squared minus 2as, or the standard final velocity equal to initial velocity times acceleration plus the acceleration that time. So you know all of that. But let's take that simple, the more clear case, and where you had the horizontal motion, which we just use S is equal to ut plus half at squared. But regardless of any of that, we never considered the effect of gravity. And in practical scenarios, if you would throw something, you always see it going down this way to and hitting the ground. That's because the Earth has gravity and it pulls us down. Unless you project something at an incredibly high velocity, you're not gonna exempt yourself from it. Literally, you will not escape Earth's gravity. If you had something super good, then you just escape gravity and go. If not, the Earth is curved, so you'll actually be following the curvature of the Earth at the very least. But for simple motions, motion distance is not very large with respect to the curvature of the Earth. But simple motion, we've seen you throw something, it's going to head down, right? And if you were to throw something to another person, typically we like to project it upwards so we can get that additional distance. And that's observed information. But I want to study that a little closer, and I want to show you what's going on with the math behind it. Hopefully, if you can intuit how we've arrived at it, if you can memorize the formula, great. There are exam questions in some curricula that seem to want you to memorize some of these, but you don't really need to. The concept is what you need. You should be able to work it out. But anyway, I've kind of drawn up some stuff here, and I'll explain what it is. So imagine if it's me and I'm going to throw this ball or a particle, and I'm going to project it out with a particular velocity, right? So it's given that initial velocity, and it's at an angle. I know I'm throwing it at an angle, and I'll work with that angle because a special case of it is if it was a horizontal shot, and if another special case if it was a vertical projection. So I have an angle theta. I'm given that much I know very well, and I project it. And I'm going to first of all break this whole thing down into vectors. So let's say I'm not at the ground. I'm at a height. That's the h here, and I project something out. And the moment let me just say I'm projecting it out with a particular velocity, you can call that u or u naught, however you want to define it, right? But that's the moment, the very instant it has left my hand, whatever happens to it begins to get resolved into two components, right? In a free body diagram. As soon as it's that instant where I have let go, that very tiny instant, there is nothing else acting on it except the force of gravity, and that's there. And I'm tracking its displacement with a green vector S, right? So I have displacement vector, and I've broken that down into two. So at any given point, here's how it would work. I mean, gravity is only acting in this direction. It's the only known force acting on it. There's no air resistance. So I want to be able to write these things first, and I can actually very safely say here, where was I? So I can very safely state something here. I know that at any given time or at any given point, in this two-dimensional xy plane, the vectors of this function of these variables, so u of x, now you know velocity is initial velocity time plus acceleration due to gravity. I'm If it was free fall or whatever is the acceleration in that direction, the direction of x, there is no acceleration at all. So I could probably just say u of x is basically its initial velocity u times that cosine theta. I hope you're with me on that. Velocity along y, there is acceleration. And acceleration would be negative here because of directions when we're with vectors. So this would be u of sine theta plus at, actually it's negative g times t. This is, I hope this is clear, right? And I just added some numbers here saying, these are of interest to me. R is sort of how far I can throw it. I measured this as D, saying that effective distance. So you could flip it around and say, no, this should be R. But this is, if it was a ground to ground, if it was sort of surface to surface, like a missile, I'm assuming that's the point of interest. If I'm throwing it, or if I'm shooting it from up top of a mountain, then it's probably this. And if it's a bullet from a handgun, you know that the handgun is not on the ground. So you probably are interested in this little bit as well. So I kind of gave it, these are sort of the velocities at these points. This is the maximum. So call it the elevation, the maximum point at which I want to see what the velocity is there. And maybe I want to check what time it takes to get there, the maximum height. I might want to check what time it takes to get to this distance, what time it takes to get. So these are just items of interest, right? So I have this. So I'm not going to do our standard S is equal to ut plus half at squared. That's a very, you did it in vertical motion. You did it in that horizontal motion without gravity, one dimension. So you didn't have to do vectors. You were doing scalars. You cannot do that here. So this is purely vector. This is why I think I like this. And because I'm going to work this out, there's two dimensions. I'm going to work out in both dimensions to see where I get. And likewise, I have my displacement vector, which I've now resolved as well into an x component and a y component, right? Acceleration obviously is a vector, but it only has one component, which is its y component. So how would I state this? And I want to state this, and I want to start off with my y-axis, and I could use that same s is equal to ut plus half at squared. Let me use better chalk here. I'll probably say s of y. I might need more space because let me use more space. Let me get a little more liberal with this. What shall we do first? Let's do the x-axis, right? So okay, it's ut plus half at squared. We know u we've done that because at in that direction is a0. S, so that's there. So this would just be u times cosine theta times, actually, to avoid confusion, because I don't want you to think cosine of theta t, I'm going to write this as u times t times cosine of theta. So far, you're with me. So at any given point, I can write its corresponding velocity vector and time. Okay. What else can I write? I can write about I also know my s-axis. I hope I have the space for it. So that's a lot of trigonometry going in here. This would be ut plus half at square. U of y but at any time this should be cosine, no, this would be along the vertical angle would be sine theta times t. Again, I to simplify it for you, u times t sine theta. Acceleration is negative, so it would be 1/2. Okay. Okay. Let's see where we go with this. I think we have our math is right. Okay. So our equations for velocity are correct. Velocity at a given point is initial velocity, factor of initial velocity and angle. Velocity at any given point is initial velocity factor and then acceleration times time square. I think we have this correct. Okay, so we've got these two. I want to quickly play with a few things to see what's of interest to us. We did like to see how much time would lapse. So as we move forward, so this is, you know what I should do? I should probably also, you know what, maybe I should just get a little more correct. So this is y displacement, but I already have an h factor here. So maybe I should write sy is equal to h. Now, obviously, if I was starting from the ground, h would be 0, hy plus. That would be a better value of sy, isn't it? Yeah, because the initial value already, there is an h built in. So sy sort of has that h in it. Okay, so now let's move from here. So clearly sy is increasing. Time progresses. When we get to this area, and then you can see it's curving down. So that means somewhere on top here, there is no further vertical velocity. Can I write here at max elevation u of y equal to 0? With me? Which means zero equal to u sine theta minus gt. If I flip these around, I should be able to say time at max elevation should be u by g sine theta. How does this work out if theta was 90 degrees and I was shooting it up? Would I still get u by g? I think so, because acceleration, negative acceleration, time is velocity by acceleration, because that would be correct. Theta would be 1 because it's 90 degrees, and it would be, it would check out. This is correct. Okay, so we know that. We know that. Okay. Okay, if I can solve this, can I then say at this time, what would sy be? Good, isn't it? Then you could say sy, or rather, the right way to say it is maximum elevation maximum elevation, right? So that would be the distance E, substituting into SY is H plus U times U by G sine theta, U by G sine theta, minus 1/2 G times T square U square by G square sine square theta. H plus U square by G. So I have this U square by G. Am I getting it right? Sine theta. But that's sine squared theta. UT. No. This has to be squared theta, isn't it? Because it's UG sine theta and there is sine theta here. So this is UG sine squared theta. And that is the G, and this goes away. This is 1/2 U squared by G. Look at that. Sine squared theta. Well, those terms would simply give me be H plus U squared by 2G sine squared theta. So if I was not H meters above, if I was right at the ground, then maximum elevation would be that, because H would be 0. But because I'm higher up now, I will arrive at slightly higher. Now assume if it was that regular calculation that we had of a vertical motion, sine theta is 90, sine squared theta would be 1 as well. What happens? I mean, would we be able to calculate our S here? Yes, we would know V square is 0. V is 0 is equal to U square minus 2GS. And absolutely, so S is equal to V square by 2G. Checks out. So we are good. This looks good. So you know the time that it takes. You know the maximum elevation. You can calculate that as well. What else can we do and play with here? Well, one simple thing we could do here is, if the time taken for an object to go up is typically the same under gravity would make sure it comes back down at the same within the same amount of time, regardless of the mass of the object. So if we did push an object up, and you can do the math, it takes the same amount of time for it to come back down either way, because in one case, initial velocity is going to 0, the other you get 0 velocity initial coming down to some final value velocity. So we can safely say that if TE is so much, TD is equal to 2 times TE. So we can also do that part. So we can say TD is equal to 2 times TE, which means it's 2U sine theta by G. With me on that? Just twice that. So that would be the time for the object to come back here. I'm getting somewhere, am I not? Wow, this looks good. This looks good. If I know TE, I can also find out E, because E is just S of X, isn't it? So I can bring that here, and I know the distance at which my maximum elevation comes up, right? That's actually E is that. So if I call this AE distance is, I think it's just an SFX at D. Maybe I call it S of E, whatever. You get the point. I could do this substitution and I could get, what could I do here? That would be U times U by G sine theta, and then the cosine theta of this. Theta is given, U is given, G is known. I can find that out. That was one. So I'll just write this as U squared by G. You can possibly also modify this because sine theta times cosine theta is nothing but sine 2 theta by 2. So I could write this as U squared sine 2 theta by 2, and I think I can do this. That is a possibility. Well, anyway, so we know this distance, that time. Can we now use this value of time to calculate AD, total distance D? If I wanted D is, one says SD, I wonder what that would be. Well, the math checks out. It'll be exactly twice that, isn't it? Because the only factor is 2. You would get D is, imagine I'm bringing that here, D is nothing but, that's U times 2U, so it's 2U squared, right? U from here and 2U, T, sine theta cos theta, sine theta cosine theta by G. 2 sine theta cos theta cosine theta is just sine squared theta, so it's equal to just U square sine 2 theta by G is D. There's a very interesting, so this is a trigonometric identity. I think it's important to know that. Otherwise, you might be tempted to think that if theta was 90 degrees or theta was 0, these values would all become 0. Well, not really, because just because theta was 0, it doesn't mean that you won't get a value for a E, right? A E is not going to be 0. So if you look at it from this perspective, you might have a better appreciation for that, right? But let's look at D. This is interesting. I like this very much because if you look at D from this point of view, where do you get the best value of D? And that's usually when sine of 90 degrees will give you the maximum value, right? In the case of straight, if it's just going straight up, completely different, because sine of 180 would be 0, you'd be tempted to say that your D is 0, which is true because it's going straight up. There is no D, which makes sense, right? It's going to come back straight down. So that checks out, but you wouldn't check it out for if it's sine 0, which is if theta was 0 and it's going this way, then again, you would get a value 0 here, which is not true, because in reality, if that's the case, you wouldn't cross substitute them. If that was 0, then automatically this equation doesn't hold. So you're not going to be able to take the time value of time when it is 0 and substitute it into another equation. So just FYI on that. So these substitutions are all, at that fine point, but you could technically do a limits problem on this and arrive at a value. But back to where we are, if this was 45 degrees is where you'd get your maximum distance. So in order to get my maximum coverage, I can shoot my projectile at 45 degrees and then I would have my best value, right? Obviously, in the special case of 90 degrees, it's just U squared G times 0, which means there is no distance that you cover. right? For elevation, that checks out pretty well, because if it was 90 degrees, you'd have your maximum value of 1 here, which gives you u squared by 2g as in normal vertical. If it was 0, again, you'd have an issue, because when it was 0, this part becomes 0. It pretends like the elevation is h, which is true, because it stays at that point and then gravity wants to bring it down. But if that was your ground 0, it just stays there. So also valid, right? That substitution is valid because you're keeping it within this equation. You're not bringing that 0 case when you try to cross substitute with each other. If you take a 90 case and substitute there, you have a problem. If you take a 0 case and substitute here, you have a problem, because when you make something 0, and then attempt to substitute, that's not a legitimate. It's like saying I multiply every equation with 0 on either side. What happens? Well, that's not how to solve equations. You get 0 equals 0. No. So be careful. That's why those special case substitutions don't hold. Okay, so what have we? We've pretty good. We've gotten thus far. This is really nice. But now let me also want to say, what would be my velocity at which it would land here? Now that's an interesting one. What do you reckon the velocity is going to be? Well, that should be fairly simple. At d, so I've got an e, I know that. So I know d, I know the distance e, I know the elevation, distance to e, I know the elevation, I know the time. If I want to calculate the velocity ue, well, since the vertical component is null, I know that just the horizontal component exists. So that's a fairly easy one, right? I could just say it's, at this point, it's just u sine theta. That's the only thing that exists. That's fairly straightforward. When it's coming back down here, what might be happening? It would be, again, I would use the same equation, just the time that has passed to get to d, right? So that's fairly good. Cancels out, you just get u sine theta. So it's the component for u is, they both check out. It basically results in the same value as u here. So that also seems to make sense. So everything is very symmetric so far. I hope you understand that part, right? So at ud, if I substitute the value td here into that equation for time up in the corner, the g cancel out. You get a negative 2u sine theta. If you have u sine theta, you get negative u there. So the answer of uy would be minus u sine theta. That's because it's opposite direction. Remember, here the velocity was upwards, here the velocity is down. So it checks out that way. That's the negative value. And here there is no function of time. This remains the same. The vector will be resolved between the negative u y and the positive ux, and you get a vector down this way. So it basically strikes back on the ground. If I was shooting at ground level, it comes back there. Now that I'm elevated, what's going to happen there would be an interesting question. How would I work the math out there? Right. This is where it gets a little bit tricky. You could just say, well, you can extend this and say, well, at this point, I could still say the displacement component, right? So my horizontal displacement component is there. There has not been anything happening there. It's just that only function is I don't know the time there. Well, how do you find time here? I can go back here because I know my vertical displacement is a negative h. So if I got this case and said wherever sy was negative h, or if sy, so if these canceled out in that, this point is now down h, right? So this would cancel out at r, right? Think about it this way. When you've reached r, it's like a special case, right? It's like this case with h0, for example, and e0, right? Or e is just equal to the maximum elevation. Sorry, it's like d, where it's basically back at h, right? Your sy at d would just be h, because you'll see that these two values will come back to what they are here. So at this point, Sy, so Sx is the D, Sy will just be H. Which means if I'm going down H, what would I be doing? I could say this would be, let me see if I can work the math out here and see if I define Sy backwards. What would I get? If Sy on the vector is a negative H, what happens then? And I get an H here. Let's say u sine theta of u sine theta times t and a minus of g by 2 t squared. There we go. I can write that as a quadratic equation. Use a quadratic formula and solve it. And I should be able to get a value for time, which I can then substitute in here. It's going to be a pretty long trigonometric value, but I think you can resolve it and obtain that. So that's I'll let you kind of figure out that math. I don't want to make my board any messy. But here's the second part to this, right? And this is because we studied work, we studied energy, and we studied all those cool things. What I want you to also consider when you look at a problem or anything that involves this is one other factor. So now that you know how to use the vectors and get some values for velocity, etc., you can manipulate the math. But I also want you to consider the second part of this, which is energy, right? So at this very point, if you have a velocity of u, and I'm going to define these points as A, point E, point D, and point R, and I can say at point A, what happens, I have kinetic energy, and that kinetic energy is half times mv times u squared, right? I'm using absolute values, not using the vector, and I have potential energy, PE. Maybe the right way to do it is just summarize. I'll add the two of them with, maybe I'll write total energy, total mechanical energy, okay, is equal to, let's just say kinetic energy half mv square, mu square, right, plus I don't know if the colors are obvious, but that should give you an idea. So if you use this this perspective, imagine what you can do. So this would be at A, right? Let's just say this is at A. Perhaps here, if I wrote point E, which is my next checkpoint, I would now write total mechanical energy as, there would be a velocity, right? Whatever that velocity is, of mass hasn't changed, U at E. Now, we know from a previous calculation that U of E was just U of A cosine theta. So you can see the relationship is building up. And add mass times G. That hasn't changed. But H has changed now. It's a total elevation, E, which in reality is just H plus some elevation here, right? This is, if I just call this H plus something here, maybe Y max, something like that. You can now say that's the elevation. Which is really easy. So now see what relationship you can build. You literally can equate potential at the energy equations. You know from your previous calculation, UE is just UA cosine theta because there is no vertical component there. You can solve it. Energy is conservation, which means you will now be able to calculate this in another manner using energy, right? If you know velocity, you can calculate using energy. But I'll extend this a little further, right? We have two more checkpoints there. Checkpoint 3 is point number D. Again, what's the total mechanical energy here? We'd be interested to find out. It's coming back down, potential energy. So this would be very similar to 1 over half m ud square. We know ud square is just a negative of ua square. We proved that in the previous calculation because the y component now is facing down. You got the negative value. X doesn't change. The vectors, the total vector would be just this one, but with a negative direction. So you'll have that, but magnitude doesn't change. So you could equate those two. And what happens here? Well, this is m, g, h. So you can still, given one of the velocities, you can equate this and find out the last one. So that's another one. And then finally, if you look at point number R, what happens here? You have some new velocity with which you're going to find, let's say, half m. You clearly do not know this velocity, u at r squared, but you know very well that you're down on h. So this is really easy, and this is just going to be mg. So think of this, and all of these are equal because energy is not destroyed, conservation of energy. So if you had this, you can estimate that, isn't it? Or if you knew this and the elevation, the maximum, you could estimate the final velocity at r. What would be that final velocity? But this is not a vector quantity. You can resolve this vector, like I showed you in the previous case. You can get to this place, resolve t, then get a component of uy and a component of ux for at that point r, and you would actually be able to calculate the angle of that. So you can even determine at the angle at which this particle would strike. If it's a bullet that's shot from my height, I can determine what angle it would fall at the ground after a certain point. But that's the calculation. You can play with the math. It's a lot of math. The trigonometry part, if you know it and you've studied it, makes it super interesting because you can play with those identities and see how you can manipulate the sine and cosine and rewrite the theta angle. We know distance is u squared by 2g sine 2 theta. You could just play with it and write theta as the inverse of distance. So if you shoot something out 5 kilometers, what would be, and if you could project it at a beginning velocity, how do you calculate that? Easy. Figure out what impulse is needed to take that mass from 0 to some velocity, fire it out at that velocity. What angle do you need to point your barrel at, so you know how to get that distance? So you can play with a lot of these things. But the fundamental idea is that distance maximizes at 45 degrees. Hopefully this kind of gives you a full view of this, of what's going on. Maybe the other part is to also remember that this trajectory typically, and if you write that equation for the Sy equal to u sine theta times t minus g by 2 t squared. And if you find t as a function of Sx and substitute it, basically you'll get the cosine theta part coming here, which is, I think Sx is t times u cosine theta. So t would be sx divided by u cosine theta. So you'd have that cosine theta coming down here. You'll have cosine squared theta coming here. Either way, in terms of sx, this would be sx, and then you'd have u cosine theta. This cancels out. You get a tan theta, and then this would be nothing but u square cosine square theta times sx squared. And if you look at this as a plot of y and x, then this is basically constant. You get tangent of theta, and then this would be a constant. G is constant, u is constant, and only x and y vary. You could actually write this as a parabolic equation of constant k times x, y is equal to constant k1 times x plus constant k2 times x squared, which is the equation of a parabola. So if somebody asks you what is the trajectory of a parabola, trajectory of a projectile, a body that is thrown freely, not straight up any other angle, it is a parabolic trajectory, right? So if you don't know, that is the equation of a parabola. Hopefully your mathematics curriculum has covered this and you're able to identify it, right? And you can see here, k is nothing but tan theta. Right? And k2 is nothing but negative g. Remember, the negative g is because of the direction it's acting in, u squared divided by 2 times cosine squared theta. There are some places, very annoyingly, who expect you to remember these. I haven't seen very many that want you to remember this relationship, but I have seen a lot of places in Hong Kong, in Singapore, in India, many curricula where they give you an equation like this for a projectile and ask you to calculate the angle at which it was projected. It's rather painful, but if you kind of remember the intuition behind what we did here, right? We got this equation, we substituted the t for um, the x-axis, and then you got that part. It was fairly easy to say that this is tangent of theta. When you see this component here, when you see the squared, you know that that's the more complicated portion. And that's really, if you look at, and if you try to analyze, as x increases, there is that the negative value of this also increases. That makes y change a lot more because this has a greater component. And remember, tan 45 is 1, right? So another way of remembering that 45 degrees is the angle to get the maximum y is here, right? So some of those interesting points that you can gather from this. Hopefully this gives you a nice insight what the free body does, how the vectors play, and how it ties to the energy, and just kind of married all of these together. So if you see problems like this where somebody gives you the projectile, maybe not this kind of an equation and asking you to remember the formula, but if they just tell you, oh, I have a point here somewhere and it's I don't know, 8 meters away, and when I go up here it's 11 meters, and I've measured the velocity here u to be equal to, I don't know, 30 meters per second, and then ask you to find UR, then what do? You just go to your energy formula and determine it, right? Or if you don't get one of those, go to your vector formula and determine one of the velocities somewhere here, like this one I said is just u cosine theta. Once you did, you basically take the UA cosine theta and you get UE, and then you can determine elevation. So you can play with these a little bit. Hopefully you remember this. Try to do some problems, try to imagine yourself shooting different bullets from different heights, see what happens to these at different velocities, and see what you get out of this. But hopefully it gives you clarity. I'm going to put this right at 6a, core concept 6a. So after free bodies and free body and equilibrium, I'm going to put this because this is really an extension of that concept, and that I've just brought in the energy just to make it give you a real world example of this. And otherwise, I've done concept 7, which is, I think, elastic spring. So I'll see you in concept 8 after that. Wonderful. Thank you.